can one cut stones with laser saber? How molecules are changed? If you make a molecule to explode or break on pieces with a laser or with a light, how many fragments will be created? If there are several of those, how can one find which one will be generated or in which proportions? So in the high school chemistry we had this word isomers, and if reaction creates several isomers, how do we know which of them will be generated? Ideally, it would be great to control formation of isomers by tuning the frequency or intensity of the laser and direct reaction to desired product.
And upon photoexcitation, there are several pathways. One can recombine, one can go to higher state, one can break the bond.
So we are going to make our microelectronics smaller and smaller. We need to have so many transistors per square inch, or like on our memory it was 100 nanometers transistors, 30 nanometers, 18 nanometers, 9 nanometers. We are trying to get elements of computers smaller and smaller on a chip. And in addition to semiconductors, for the healthy circuitry, one needs metals and insulators. So nano semiconductors are fine, nano metals are fine, but nano insulators was a challenge, because if we have nano thick or nano thin layer of insulator, it starts leaking charge. If you do standard silicon dioxide, the material from sand, if instead of oxide of silicon we use oxide of these heavy elements like lanthanum or several other, it will be ideal insulator on monatomic layer, so really thinner than a nanometer. In order to fabricate these nano layers, there is a quite versatile experimental technique, chemical vapor deposition, or more specifically laser-assisted chemical vapor deposition. So first, one chemically synthesizes metalorganic complexes. Example is here, metal in the center and this organic ligands around. This substance is very easily sublimed, evaporated by moderate heat. And then there is a vacuum chamber with substrate, and one injects this gas of the metalorganic complex. Then one breaks it on pieces with laser pulse. So the princes of the metal get rid of chains of this organic junk, and then the pure pink metal deposits to the surface and creates monatomic layer of metal. And then we just expose it to the oxygen and automatically form oxide.
So maybe it is the most interesting thing. We are considering photoinduced decomposition of metalorganic complexes with lanthanum and some organic shells. So it is the dynamics upon continuous irradiation with train of pi pulses, which is used as an approximation to mimic CW high intensity irradiation. So it brings rich dynamics that can be interpreted either as decomposition of complex or as metal cluster facilitating some rich catalysis for these hydrocarbons.
We did start with the pink metal, and that was the beginning. The 5 carbon molecules which are ligand, so organic ligand near the metal ion, and then we repeatedly excite and de-excite it so that it accumulates kinetic energy and experiences breaking on pieces. So it breaks carbon bond and then experiences rich chemistry, which can be also interpreted as metal ion catalyzes rich hydrocarbon transformations.
So if we look onto stages of the photoreaction and convert masses of the fragments developed at each stage into this distribution, then first stage we go from the heaviest component to the like this, from 5 carbons to 3 and 2 carbons. You see these components. If you go further and continue the dynamics, so we see here this C2 component, and if you continue the dynamics further, there is a complete departure of these hydrocarbons from lanthanide, and this helps to compute mass spectrum of this photoreaction. It does agree with experiment to some extent, and the application is thin film deposition for computing.
Experiment. So we hope by further developing of this method, of this technology, computational technology, we can predict more and more reactions, and maybe do reactions that haven't been done yet on experiment to show some predictive power.